Hi guys, hope all of us are doing great. My name is Ernest and this is Ernest Sciences and Mathematics TV channel. Our discussion today is going to be centered around the concept of an electric field. And of course, this is going to be supplementing on the previous video we had done on the various characteristics of an electric field and how we can represent the electric field lines. Now, suppose I just give it in terms of a summary form. I'd say that basically a charge, an electric charge is going to be given in terms of either positive or a negative, and we're going to have the field lines which are going to be lines representing the electric field surrounding these particular charges. Perhaps I can just move this one down here, and there's a way in which we are going to represent these specific lines considering those ones which are going to be far away from this specific charge, near this specific charge. And of course, there's an aspect of symmetry which we are going to consider in order for us to represent the various lines. Now, these lines are going to radiate from the basic, of course, procedures which we have done, or rather said, in representing the various lines of the electric field. We said that for the positive charge, these lines are going to be radiating outwards. They are going to be appearing in this specific form or spherical form, and therefore we can represent them using this particular representation which are basically given on the board. Now, one of the characteristics of these lines which we said they are not going to be crossing one another or intersecting, and therefore they can be given in summary form using these two specific representations which are given on the board. Now, an electric charge is going to produce what we refer to as an electric field, and of course we can be able to quantify this specific electric field indicating its specific strength that is going to be created due to the presence of these two specific charges, and we can measure this particular force which is going to be experienced by a charge due to the presence of another one by trying to use what we refer to as a test charge. Now, in this case, I'm going to use an illustration in order to show this specific example. And this is going to constitute of a system of these two specific charges for Q and the Q naught given as such. Now, this Q naught is going to constitute of a positive charge, and this is going to be given as such. Now, this other one is going to be referred to as a source charge. So I can perhaps give them in terms of this specific naming. So we're going to have this one as a positive charge given as such, and this is going to be referred to as a point charge given as such. So in this case, we're going to have this positive charge given as a point charge at a particular distance, and the point charge is going to be given as Q naught, while this other one, which is a source charge, is going to be given as a Q. Now, there's going to be a force of course, being experienced at Q due to the presence of this specific Q naught, and the Q naught is going to be taken to be infinitely small, so that the field it generates is not going to be, of course, affecting the source charge as we have indicated. We can give the separation distance between these two specific of course charges as let's give this one as a day, and then we're going to see that we can be able to give the electric field for this specific system of charges by using the general representation which we had given for representing an electric field, which was basically given in terms of this specific notation, and we said this is going to be a vector quantity. Therefore, we're going to give it in terms of that one, which is a ratio between the force experienced and the charge. The force experienced by that specific particle and the charge given as such. And this is going to be basically the charge of this particular proton, which we have given as a point charge, and therefore it's going to be a proton indicated as such. So in terms of a formula, we can indicate this one in terms of the electric field is equivalent to the force being experienced all over the charge, which is of course a test charge or a point charge being given as Q naught, and this is going to give us the representation of an electric field, of course, being experienced due to the presence of that specific test charge given as such. Now, suppose we had this one given in terms of perhaps the source charge is a negative one, then therefore that specific force is going to be directed in that particular direction, and we're going to represent the vector, the unity vector being given in that particular case as such on the test charge. And therefore we can be able to create an electric field which is going to exert a force on the test charge, and this is going to be given in terms of F sub E being given as such. So therefore taking in mind of that specific kind of a force, we can be able to represent the force being experienced on this specific test charge given as Fe is equivalent to E Q naught, and I can just give that one in terms of that specific representation. And of course, whereby the Q naught, as we said, is going to represent what we refer to as a test charge. Therefore, considering this, we can use the Coulomb's law in order to represent the relationship between the electric field and this specific test charge. Now, from this specific representation, we can see that we can have the electric field being given in terms of the ratio between the force and the test charge. Now, from Coulomb's law, we had said that we can expand this one to have 4 pi epsilon naught, and then we're going to have the product of the two charges for the source charge and the test, or rather the point charge being given as a Q naught all over the separation distance, which of course we have given in terms of a D. So let's just have this one as R for clarity, and then we're going to have this one using the unity vector which we have given on the other side. And therefore, in order for us to have this one, we are going to have this one divided by a Q naught. And therefore, if we try to look at this one, this is going to be simplified into a version of electric field being given in terms of 1 over 4 pi epsilon naught, and then we're going to have Q. So this is going to cancel out with this one, and this is going to be Q over R squared, and then we're going to have this one a vector being given as such. So this is going to be a representation of particularly, so this is going to be given as Q, and then we shall have the whole of this one over the square of R given as such. So this is going to represent the electric field, of course, being experienced due to the presence of this specific test charge, or rather that point charge being at that particular point. And this is going to be, of course, the formula we can use for representing that. Now we're going to see that using the principle of superposition, which we have discussed in some of our videos, this is going to be true for the case of an electric field due to the presence of a particular charge, and this is going to create a sum of all the other electric fields which are going to be present due to the presence of other charges. So we're going to indicate this one as the electric field as a summation of the other fields being created by the presence of other charges, which can be indicated in this specific form. And this is going to go on, of course, to the n number of course, charges which are going to be present given as such. So this one can be given in terms of just a summary, whereby we're going to have this one as a summation from I is equivalent to 1 to n over this specific range of course, fields which have been created due to the presence of other particles. Now this one can be expanded as well to accommodate for the concept of this specific representation, and therefore we're going to have this one being represented in terms of the summation from I to 1 to n number of particles for, of course, which are going to result in various other forms of these particular fields which you have listed, and then that is going to be Q naught all over. So we're going to have that one as the square of R, which is a separation distance. Perhaps I can give it in terms of this specific form, and the unit vector is going to be represented as such. So this is going to be a general representation for the presence of other particles which are going to be having an effect of the various fields which we have mentioned. And of course, that's going to be assisting us identify a way of representing an electric field in a system of particles which or charges which we have mentioned from our previous statement. Now, in our next discussion, we're going to just use a similar example or a particularly relevant example, just like the one we had used for the principle of superposition, in order for us to evaluate a few cases of this specific aspect of an electric field that is being experienced by particles due to the presence of other particles in various systems. So in this particular case, I'd like to request our members to kindly check our description boxes for various links of other videos. Subscribe and engage us in the comment section so that we can be getting updates on various discussion we do in mathematics and sciences. So that is it for now, guys. Bye, God bless you. Catch us in our next video.